and welcome to this webinar. Today we wanted to show you what's new in IBM SPSS Statistics version 31. My name is Astrid Cook and I'm an analyst here at version 1. Now in version 31 there are numerous new procedures and enhancements. So we've broken this webinar out into sections. And we want to start by showing you how to locate, download, and install extensions. Then we'll review the new procedures. So we have proximity mapping, distance correlation, time series filters, conditional inference trees, and stats earth. Now these last three are coming across from the extensions menu. Finally, we'll talk about more changes that will make IBM SPSS Statistics easier to use. So let's review how to find, how to download, and how to install extensions. Now to get started, go to the extensions menu and click on Extension Hub. This brings up the Extension Hub dialog box. Make sure you click on the Explore tab, and there's a search area. So type in the name of the procedure. Here I've typed in time series filters. This will bring up the time series filters extension. You can tick Get Extension, and then click OK. Now, the next thing is the license agreement. So a license agreement will appear. Make sure you read through it. You can accept it, and then click on Finish. You'll receive a message that lets you know that SPSS is downloading and installing the extension. Once that has completed, you'll receive a message that lets you know that the extension has been installed, and then you just click OK. Once your extension is installed, you'll receive a message that will show you where to find it. So here it's letting me know that the dialog for time series filters is installed to the Analyze menu, Forecasting, and that's where you will find time series filters. So you can see the new item that's been added here on the Forecasting menu. If for some reason you encounter any issues, you can also pick up the extensions from the IBM SPSS Predictive Analytics page on GitHub. So here I've done a search for Stats Earth. Again, this is a new feature. When I click on the name Stats Earth, it'll bring up another page. And on that page will be a releases section. Click on the latest button. It will actually bring up the extension here. If you click on the name, it will download the extension for you. And you can install a local extension bundle. If you do have issues, you can also, of course, speak to your IT team. Now let's dive into the new procedures in version 31. So let's look at proximity mapping. So proximity mapping is a visualization technique that spatially organizes multivariate data to reveal relationships among objects. Previously called multidimensional scaling, it clusters similar items together while separating dissimilar ones, making patterns in complex relational data clear. So this is the ProxMap procedure, and it's going to give you greater flexibility than ProxScal, accommodating various input types and multiple proximity sources. To access proximity mapping, go to Analyze, Mapping, and Proximity Mapping. So here's our challenge. We want to assess how consumers perceive the affordability and healthiness of different drinks. So we have things like branded diet soda, branded energy drinks, branded smoothies, branded still water, branded sugar sweetened soda, versus all the store-owned brand versions of these drinks. Now, proximity mapping will help us because it will cluster similar items together while separating dissimilar ones. So we can see patterns in complex relational data. So here you can see we have affordability and healthiness. And of course, you can see, for example, if we're looking at branded still water, you can see that here. It's positioned near the healthiness arrow, implying a healthy perception. If we look at store-owned brand sugar sweetened soda and store-owned brand energy drink, we can see that up here. So these are closer to the affordability arrow, suggesting they're viewed as more affordable. If we look at, say, for example, branded energy drink, branded sugar sweetened soda, you can see that they're further from both arrows, and so they're seen as less healthy and less affordable. So let's see how this works in SPSS. So to get to proximity mapping, you'll need to go to the Analyze menu, Mapping, and Proximity Mapping. Now, when you open up the dialog box, you can move the variables in source here. And then, of course, because I have brand code as object labels, I can move it into the object labels box. We've got data type options. It's proximity data or multivariate data. So we've got multivariate data. Make sure that you add the source. Now, I wanted to point out as well that if you click on initial, you can control scaling. You can control model settings, restrictions, criteria. You can control the number of dimensions. For output, you have output for data, for initial, for model, restrictions, supplementary, and criteria. So you can get things such as summary, diagnostics, iteration history, stress decomposition, and then for graphs, iteration history, and stress plot. So when you're ready, when you set everything up and you click on Add Source, you can click OK, and that will run the proximity map. Now, in the output, I'll be interested in the biplot. And of course, you can see the biplot here. So the blue line represents affordability. Red line represents healthiness. If we look at the blue line and we look at the top of the blue line, we can see products that are near the top. So we look at store-owned brand energy drink and store-owned brand sugar sweetened soda. So they're close to the affordability era, suggesting they're viewed as more affordable. If we look at branded still water, which is down here, branded smoothie, close to the healthiness arrow or the top of the healthiness arrow, suggesting they are viewed as healthier. If we look at branded energy drink and branded sugar sweetened soda, they're farther from both arrows, so they're likely seen as less healthy and less affordable. So you can see that when we look at these products, some are store-owned brand, some are branded, and we look at the variety of products, we can see the similarities and dissimilarities in a map. Now let's look at running distance correlations. SPSS now has distance correlation. Now, to find it, go to the Analyze menu, select Correlate, and then select Distance Correlation. This will bring up the distance correlation dialog box, and you can see you have an area to place your input variables. You can choose criteria, options for print, and plot options. Now, distance correlation has advantages. So it can detect linear and nonlinear relationships. And it also assesses variable independence more directly than the Pearson correlation. Distance correlation works with random vectors of different dimensions, making it ideal for complex data sets, and there's no requirement for the data to follow a normal distribution. Also, you can, if you want, use it for feature selection. It could help you identify relevant variables even in complex relationships. There are some considerations. First of all, it's not scale invariant, which means standardization could be required. You will see in the dialog box there are options to standardize the data. There's a high computational cost. It can be resource intensive when working with large data sets. And just make sure you pre-process, check your data, and address any missing values. Now we're going to use some sample data. This sample data set is actually installed with SPSS, so it's called bankloan.sav. And in this data set, we have information on customers' age, years with current employer, household income, and debt to income ratio. Now we're interested in these fields and understanding these fields because we could use them to evaluate risk. And we want to identify strong dependencies among these variables to better understand borrower traits that could affect risk. But we also have an additional question, and this is whether or not the debt to income ratio is related to all variables or is it independent? Now, when we run distance correlation, we will obtain the distance correlation. We can obtain a permutation-based p-value, distance covariance. This quantifies the strength of dependence between the variables. Distance variance measures variability within individual variables to normalize the correlation. And in terms of data consideration, only continuous variables can be used for analysis. You need a minimum of 2 continuous variables and a maximum of 30 variables are allowed. Now, when we run distance correlation, we'll get quite a bit of output. but you will get descriptive statistics. So you'll see each variable, the count, average, standard deviation, and minimum and maximum values. You'll receive a table of distance correlation coefficients. Now, what I've done here is I've used color scales just to add some color to show the larger distance correlation values. And what we see is employment and income demonstrates the strongest distance correlation. You can see that here. Age and employment, age and income indicate slight dependencies. And this could be from gained experience or career advancement over time. But if we look at debt to income ratio, you can see here, here, and here, it shows little correlation with other variables as evidenced by the values that we're looking at. So the values are near zero and the confidence intervals are very broad and they include zero. Now we also have distance correlation estimates table. So distance covariance, you can see that here. Again, I've used the color scales procedure, but this will show me the extent of joint variability. So higher values signify stronger joint dependence. What you notice is that if we look at debt income here, debt income here, debt income here, these values are very low. And it suggests that the debt to income ratio operates independently. We'll also obtain distance variance. And here I have a scatter plot. So this is going to show me the min-max normalized distances for age on the x-axis and debt to income ratio on the y-axis. It doesn't show me any pattern or clustering consistent with the low distance correlation value. And what we know is that age and debt to income ratio are statistically independent in this data set. So let's see how to run a distance correlation in SPSS. Here I have my data. The data file is called bankloan.sav. And as I mentioned, this is a file that is installed with SPSS. To get started, I'll go to the Analyze menu, select Correlate, and select Distance Correlation. And I'll move the variables into the Input Variables box, click on Criteria, and here I've got normalization, I've got options for normalization, and confidence interval percentage. For print, I want print details, distance correlation coefficients, distance covariance estimates, and distance metrics and significance estimates. For plot, I can ask for a scatter plot. I want to look at age and debt to income ratio. I'll click Continue, and then I'll click OK. And now I have my output. So I have my descriptive statistics table. So you can see the count, average, standard deviation, minimum and maximum. And here I have the correlation coefficients. Now to make things a little bit easier, I'm going to double click on this table, highlight the cells, right click, ask for color scales, and the low color value I'll make white. High color value I'll make it green just to make it easier to see. And this shows me where the stronger distance correlations are. So employment and income, here age, employment, age, income. But the strongest is employment and income. Now, if you look at the correlation estimates here and we look at covariance, I'm just going to highlight these, right click, select color scales. Now my high color value will be white this time and my low color value will be red because I'm looking for covariance that's close to zero. And what you see is debt income here, here, and here, these are close to zero. So that shows me that debt to income is independent of the other variables. I have my distance variance here, and of course, the scatter plot that we discussed earlier. So now let's talk about time series filters. Time series filtering can break down a time series into its trend and cyclical components. So time series filters have benefits because they reduce noise and highlight significant patterns. You can break down a series into trend, seasonality, and residuals, and you can prepare data for modeling or forecasting. Now you can access time series filters by going to the Analyze menu, selecting Forecasting, and selecting Time Series Filters. Now for my time series data, I'm going to apply a filter. I'm going to apply the Hodrick-Prescott filter, and this is a macroeconomic tool for creating a smooth trend in time series data. It will decompose the time series into a trend component and a cyclical component. It has a smoothing parameter, lambda, and this will control the trade-off between fit and smoothness, and you can see the recommended values for quarterly data, annual data, and monthly data. Now, when you run the time series filter, you will obtain the time series plot. So this is your starting point for examining your time series. Then you will obtain an HB filter trends plot. So this plot represents the long-term trend extracted using the filter. And you can see we've got reduced activity, reduced housing starts over the time period in our data set. So this filter smooths out the short-term fluctuations, so we don't see seasonal or temporary changes. In our output, we'll also receive the cycle plot, and this plot represents the cyclical component extracted from the data. And you can see the y-axis values, which range from -40 to 20. This shows deviations from the long-term trend. And the cycle appears to fluctuate around 0 with notable negative deviations starting around May of 2013. Finally, we have the combined plot, which we can see here. And again, we can see consistent downward trajectory beginning around May 2013 and continuing through the rest of the timeline. So let's see how this works in SPSS. So let's see how to apply a time series filter in SPSS. So before you use time series filters, or before you run any kind of forecasting model, you need to make sure you've got a date variable in your data set. Now to do this, just go to the data menu and select Define Date and Time. The data takes the format of years and months. So I'll put the first year in the series here and the first month here, and I'll click OK. And now I have my date variable. If I go to the Analyze menu, come down to Forecasting, and I bring up Time Series Filters, you can see I've moved the housing starts variable here. I've selected the lambda for monthly data, selected the filter that I want, and I'll click OK. And this will run the time series filters. So here I have my time series filter output. And as I was saying, from the start, we can examine the time series. So I can examine my data. Below this, I'll have the HB filter trends plot. So we can see really almost from the start of the data, there's a downward trend. We can examine the HB filter cycle plot. And below this, we can see the time series against the actual trend. And again, what we see is this consistent downward trend. Now we'll examine conditional inference trees. Conditional inference trees estimate classification and regression trees. And these trees use statistical tests to determine splits, and this will help reduce overfitting and enhance stability. These trees are complex, so you will get outlines and plots for better clarity. I'll show you where to find further information. So that further information will sit on a separate tab in the dialog box. And this method will produce two tree types: conditional inference trees and model-based trees. Now, to create a conditional inference tree, you can go to the Analyze menu, select Classify, and select Conditional Inference Tree. Now, as I said, if you want to get help, you can open up the Conditional Inference and MOB Trees dialog box and click on Vignettes. And you can click on any of these checkboxes to get further information. So here is some output from the tree. First of all, we'll have an outline. We can see the model here. So we are trying to understand high earners, and we're using job category, gender, and beginning salary to predict this variable. You can see the outline of the tree here. And you notice right away that the tree is split by job category, so clerical and custodial on one side versus manager on the other. And if we just look at manager, you can see it splits on gender, whereas for clerical and custodial, it splits on beginning salary. We have 6 internodes and sorry, 6 terminal nodes, excuse me, and 5 internodes. Now, you can also see variable importance, the confusion matrix, and terminal node statistics. And if we look at nodes 10 and 11, you can see there's a high percentage of high earners on these 2 nodes. And here we have the tree. So the first split is on job category, clerical and custodial on one side, manager on the other. And right away, we can see that for our clerical and custodial employees, it splits on beginning salary, whereas for our managers, it splits on gender. And here we have node 10 and 11. And what we notice is that managers, again, they are primarily our high earners. There are some high earners in clerical and custodial, but they need to start on a higher beginning salary. So we see this on node 8. So just over half are high earners. Now, there are also model-based trees, and these integrate traditional regression models with recursive partitioning. And this makes them effective when predictor outcome relationships differ among data subgroups. So there's going to be 2 variable groups, the model variables. So I could use, for example, someone's starting salary to predict their current salary. And then we have the partitioning variables. So I want to divide the data into subgroups, and I could use, for example, job category. You can see the types of models we have, but this is actually useful when we've got different subgroups. For example, we want to examine managers versus clerical staff, and these may have different regression relationships. This helps us uncover subgroup-specific patterns in the data. So here we have output, and you can see the model here. So I'm predicting salary using beginning salary, job time, and previous experience. Job category is my partition variable. So this will be the first split in the tree. You see that here, we've got clerical and custodial versus managers. But what's happening is the model is using different linear equations depending on the job category. And when we look at job time here for clerical and custodial versus managers, and previous experience for clerical and custodial versus manager, we notice, first of all, that job time has a much stronger positive effect on salary for managers than it does for clerical and custodial roles. We see that previous experience has a negative coefficient in both cases, but it's more pronounced for managers, and you can see that here. We have terminal node statistics. This is the average salary for clerical and custodial employees, average salary for managers. When we look at managers, it's a much smaller group, but it's got an average salary that's more than double that of our clerical and custodial workers. And this aligns with the earlier regression coefficients, highlighting job category as a key factor influencing salary differences among the groups. So let's see how this works in SPSS. So I'm in SPSS. My data file is called employee data. Now, this is a sample data file, and this data file is actually installed with SPSS. What I've done is just calculate a new field that determines whether or not they're a high earner. But this data file is a sample data file, so you can use it if you want to run conditional inference trees. To get started, I'll go to the Analyze menu, come down to Classify, and select Conditional Inference Tree. Now here, Vignettes, this tab, this is where you can get help. I'll click back on the Estimation tab. I'll turn on or select Calculate Tree, select my dependent variables, and again, my independent variables here. I can select options for my conditional inference tree models. I can calculate predictions. This is options for mob models. I can select options for display. So for example, I may want to see the confusion table. And then of course I can save the estimated model. And then I can click OK and run my tree. Now I have my tree output. So if we look at the model formula, I'm predicting high salary using beginning salary, job category, and gender. Here we have the outline of the tree. And here is the actual tree. The first split is on job category. So you will see that we have clerical and custodial on one side of the tree and managers on the other. Now, when we look at managers, it's split on gender, whereas for clerical and custodial, it's split on beginning salary. And down here, we can very easily see where the nodes are, or what groups of employees are high earners. So let's look at node 10 and node 11. So these are managers. Both females and males primarily are high earners if they're a manager. If we look at our clerical and custodial employees, if they earn over $18,750 on their beginning salary, over half of them are high earners. Now, if I come up here, we've got the terminal node statistics. And what you see is node 10, 80% are high earners. These are our female managers. Node 11, 98% are high earners. Those are our male managers. Here, we're looking at node 8. So these are clerical and custodial employees who earned over $18,750 on their beginning salary. Just over half are high earners. Of course, the model will also give you the confusion matrix as well as variable importance. So now let's examine StatsEarth. To get started with StatsEarth, go to the Analyze menu and select Generalized Linear Models. And you can see it's here, Multiple Adaptive Regression Splines. If you click on the Help button in the dialog box, this will give you information on this procedure, which you can see here. StatsEarth is a non-parametric regression method, and it's aimed at modeling complex nonlinear relationships between predictors and an outcome variable. And it uses hinge functions, piecewise linear segments that activate beyond a threshold to represent changes in these relationships. The algorithm operates in two phases, a forward pass to add basis functions for better model fit, and a backward pass to prune the model to avoid overfitting. This provides a sparse interpretable model that captures essential nonlinearities and interactions without manual adjustments. So it makes it ideal for high dimensional or complex data. So here's a sample data file, and we're looking at the relationship between speed and fuel efficiency. And when you look at this, it's clearly not linear. And what you notice is around 30 miles an hour, suddenly fuel efficiency increases as speed increases. And then around 60 miles an hour, fuel efficiency starts to decrease. So clearly a non-linear relationship. Consider modeling the relationship between a car's speed and its fuel efficiency. If we just ran linear regression, it would not accurately represent this relationship because we know that fuel efficiency varies. So it could vary at low speeds, such as in stop and go traffic, compared to highway speeds. StatsEarth identifies knots at specific speeds, so 30 miles per hour, 60 miles per hour, and it will fit different linear segments for various speed ranges. So we can expect that efficiency may be low, under 30 miles per hour due to the stop-start nature of city driving. Between 30 and 60 miles per hour, efficiency increases linearly. Above 60 miles an hour, efficiency may decline due to air resistance. Now, when the algorithm runs, we said there's a forward pass and a backward pass. The backward pass would eliminate segments or knots that don't enhance the overall model fit. So this will streamline the model while preserving key nonlinearities. In the dialog box, you'll see tabs across the top. So we have the Estimate tab, the Save tab, Display, and Predict. Of course, you'll make sure you estimate a model, select Yes, select your dependent variable and your independent variables. Also, if the model is used for prediction, make sure you've got a unique ID variable in your data set, and you can specify that here. So predicted values will be in a new data set that includes this ID for merging with the original data set using standard SPSS commands. Also, be aware that this procedure excludes cases with any missing data. In the dialog box, on the Estimate tab, we have Distribution Family here. So you can use logistic regression for categorical dependent variables with two values, specifying binomial here as the family. Now there's also maximum interaction degree. So you can see that here. That indicates the level of interaction where 1 means no interactions and 2 represents two variable products. If you see the distribution family here, this aligns with that of generalized linear model, such as binomial for a two-value logistic equation. Now, if you select none, You can select it to generate separate coefficients for each category of the dependent variable. Maximum terms denotes the total number of terms permitted in the final equation. You can see that here. Also, the model can be saved using the Saved subdialog box. When we run our model, of course, we'll receive the fit summary table. We can see that here, and the coefficients. So what we see is that when speed exceeds 65.2 miles per hour, fuel efficiency decreases by 0.257 miles per gallon for each additional mile per hour. You can see that here. Now, when speed exceeds 27.1 miles per hour, fuel efficiency increases by 0.529. We can see that here. When speed exceeds 58.4 miles per hour, fuel efficiency decreases by 0.583. So again, we can see that here. The model effectively reflects fuel efficiency behavior under different driving conditions. So let's see how this works in SPSS. So here I have my sample data file. To get started, I'll go to the Analyze menu, come down to Generalize Linear Models, and select Multiple Adaptive Regression Slides. Now, the tabs are across the top, so I'll start on the Estimate tab. We want to estimate a model. I've moved fuel efficiency into the dependent variable box, speed into the independent variable box. You can choose maximum interaction degree, maximum terms, distribution family, and set cross-validation folds and cross-validations. You have the option to save estimated model file. Display, you can display model plots, display response plots, display variable importance plot, and of course, you can save predictions. When you're ready, all you have to do is click OK and run that model. So we ran a simple model. And in this output, we have the fit summary and the coefficients. But I want to come down to the original scatter plot that we looked at when we started discussing StatsEarth. Here, we're looking at the relationship between speed and fuel efficiency. And if we try and fit a linear model, we have a model that doesn't fit the data very well. So we have an R-squared linear of 0.377. Now, when we look at the fit summary table from StatsEarth, and we look at the R-squared value here, 0.961. So this means that 96.1% of the variance in fuel efficiency is explained by the model. We also have the mean CVR squared. You can see that here. So this cross-validated R square suggests the model generalizes well to new data. We can also use generalized cross-validation and standardized GCV to evaluate the model. We have coefficients here, and we discussed these earlier. But I think the main point is that if I try to model the relationship between these two variables as linear, the model doesn't fit the data very well. When I use StatsEarth, I get a very good fitting model. So let's talk about more changes to IBM SPSS Statistics that make it easier to use. So we now have curated support for correlations. When you run a correlation, what you will get is a summary beneath the correlation table. Your correlation table will be color-coded, and you'll be able to see the very strongly positive, neutral, negative, and strongly negative correlations. This is available for bivariate correlations, partial correlation, distances, canonical correlation, and correlation in linear regression. You can also customize your correlation table. So if you run a correlation, you can click on the display table, go to Utilities, Run Script, and you can select the script Reformat Correlations table, and this will give you a more compact correlations table that's easier to read. There's also a new chi-square option on the Descriptive Statistics menu. So if you go to Analyze, Descriptive Statistics, and select chi-square, this will give you the chi-square test. It doesn't replace crosstabs with chi-square. It's another option. Also, you now have coefficient of variation in options for frequencies and descriptive statistics, and you've got optional control for the homogeneity of variance test when performing independent samples t-tests. So there's now the option to incorporate background images and charts. You can also set default column width. So you can change the column width, save the file, exit out of SPSS, come back in, and the column width will be there. It will be the same. There's also an option to change common properties. And so in the variable view, you can select multiple variables and adjust common properties for these variables. There are status bar enhancements. So when you select cases, you'll be able to see how many cases have been selected. You can also see unlicensed features. If there are procedures that you don't have a license for, you'll see the procedure name on the menu with a lock by it. You can click on it to get more information. License details are also now available through the Help menu. So that's everything we wanted to show you today. If you want more information, you can visit us at www.spssanalyticspartner.com. So thanks for watching, and bye for now.